This is in fact not my first time to the area. I went to a place called Leningrad in 1989 when I was a PhD student, which was very interesting. We caught a train to Estonia where we were chatting to some folks. So there's a bit of history here. Oh, well, first off, setting some things. Do ask me questions, because I'm not familiar with all of your levels. If you want me to explain a bit of math, I will try and do some explanations on the flip chart. But if you want me to do something in more detail or discuss something, I'm very happy to change plan. The second thing is that this talk is actually a hybrid of two talks. So Ben Taskar, who is, we'll get onto that in a bit, but so I've put together his talk and my talk, because he has some fabulous slides in this area. And I've added a bit more of the mathematics and explanation to it. And I do hope that's not too challenging for everyone. The other thing to notice is that all the page numbers are a bit of a mix. So don't think these page numbers here or the page numbers on Ben's slides will be in order, because I've actually changed things around. So, okay, with that, this is the source material. So Alex and Ben Taskar. Ben died young, and if you look at his website, there'll be some details. I think it might have been 2013, in the prime of his life, so to speak. But they had produced this, it's almost a book, which everyone uses, and it covers a lot of the basic material. They have a fabulous tutorial, and that's about 250 slides, and I've taken an extract from that. Some of the slides are on this excellent video lectures from Slovenia. So if any of you know about this, but you can look it up. And also the MATLAB code is currently up at Alex's website. So that's the source material for all of this. And you can get a copy of these slides, not Ben's slides, but these slides at my website, topicmodels.org. So it should be about the third or second blog entry currently. So we'll start off. They have a beautiful introduction. It is, it really goes through things very nicely. Now, a bit of context as well. I'm a math undergraduate, so you know I did all the usual stuff. So what this means is that what you'll find is that determinantal point processes, and boy, that's hard to pronounce, it's beautiful. It covers all sorts of, the ideas match beautifully with the sorts of real analysis and matrix algebra and probability. It's a wonderful mix of things. I've never seen so many things come together so nicely. So I hope you get to appreciate some of that beauty in my explanation. Secondly, so I'd been running for a couple of years. I've started up a Master of Data Science at Monash. So I'd spent a couple of years doing this, and I didn't have time to get out and do conferences. And so I turned up at ICML, and I was chairing a session, and there was a really interesting paper on this topic at the session, and I had no idea what they were talking about, and this was back in July. So I've spent the last couple of months feverishly looking at it because I found it so fascinating. So that's how I got started in this area. So the idea is very simple. When you get some results, you don't want all the same thing. You want a bit of diversity. Now, I presume an American understands what that third slide is. I have no idea why that's a Python. But here's another example. We've got some documents. We like to summarise them. Well, if we take all the top important ones in this example, we get a whole lot of information about Romney expecting to get the election. And this would have been a certain time in 2011 or 12. I don't follow the American elections. This is what you'd want. You'd want a mix. Obviously, you'd want something about Romney, but you want the other candidates. You want the spread of things. So you can see in images, in topics, there's many things. We'll see a few simple examples as well afterwards. So that's the idea. That's where we're trying to head. And I hope you can see why this is important for instance, a search engine company. We view our business, what I do in my research, as document summarisation. So for us, this is a great tool to have. So we're currently looking at what we can do with it. Graphical models let you express all sorts of dependencies, but what they don't let you do is to express this kind of diversity. People have tried and they haven't managed to do it. So that's what we'd like. We'd like some kind of model that does that. So first off, some basics. What's a point process? Determinantal point process. Determinant, and we'll see that in a bit. Point process. What is a point process? It's very simple. You've got a bunch of points, and you want to see which ones you have in your set. So it's just a probability over sets. Now, in the mathematical world, they can get this working in general measure spaces, arbitrary distributions, but we're just going to look at it in a discrete domain, and that's the standard way. For most computing, machine learning applications, this is all we do. But here we have 2 point processes, 2 point probability of this set and the probability of this other. And this is the space we'll be working in. We always have n items. Whenever you see n, that's the number of items in your space. And the full set of points is cal n. This is a LaTeX slide, if you know LaTeX, and this is cal n, cal y. So obviously there's 2 to the n possible sets, and that's what your probability is over. This is a simple distribution in that domain. Independence. Each point is distributed independently from each other. Of course, this has no diversity, but you can represent this in a graphical model as a determinantal point process. But this, this is kind of trivial. So this is the sort of thing that we want, and this is a good graphic to see what's happening. And I'll try and explain what's going on here. If we just generate points randomly, there's always going to be some clumping. It's just what happens in the random world. There's some clumping. So what we will do is points have a covariance structure between points, and so there's going to be a neighbourhood covariance for this point here. It will have a negative covariance with all of its neighbours. And anything that is considered to be far away, it's just probably got a 0 covariance. It might have a minus 10 to the 50th covariance with this one a long way away. But so by having a local covariance structure where every point is negatively correlated with all of its neighbours, you can imagine you come up with this sort of thing. So that's how it's built, but we'll get into the details. So this is it. This is the idea in the next few slides. And if you remember that stuff that a lot of people do in second year undergrad, where you learn about determinants and volumes and things, some of you may have done that. So we represent an item by a feature matrix. We've got another item. These items are similar, so their feature matrices are similar. So the dot product will be quite big, wrong way, but also the area encompassed by those two vectors is going to be small. So if the vectors have a small angle, the area must be small for that volume generated by the vectors. On the other hand, you've got something that's very different. It's going to have a very different feature vector, and so there will be a big angle between them. For these two, you know, imagine our feature vector is in 100-dimensional space. Almost certainly the angle is virtually 90 degrees. That means the area is going to be quite big. So that's for 2 points, but imagine you've got 5 objects, or 10. You've still got an area, but now it's in multi-dimensional space. So now you've got to go back to your analytic geometry or something, if you remember this. I had to brush up on it. It was probably 30 years since I've done this stuff. But here's the setup. Here we've got 2 objects with their own vector. So what we're going to do is, now this is called a gram matrix, if that rings a bell. Each row on the left side is the feature vector. And then we've got the transpose of this on the other side, and these are feature vectors. So the ith row and the jth column consists of dotting the ith feature vector and the jth feature vector. And this will be symmetric, obviously. So this matrix is a way of representing the dot products. Moreover, and we're going to work through this in a little bit, the actual volume, in this case, the volume of what this is called a parallel piped, but it's I'm going to do the 2D version. Parallel piped is going to be like we have there. In 3D, you'll have some other vector, and then, you know, everything's like this, and then at each dimension we add another one. But the volume of the parallel piped, formed by these vectors G, is going to be a determinant. And that's a basic property that we learn about determinants. We'll break this down a bit. So there's our formula, but here's an example, right? This is in a 4x4 space. And remember, what is L21? It's going to be the feature vector of the second object dotted with the feature vector of the first object. So that's our value. And if we go looking at, we want the probability of having just points 2 and 4 and 1 and 3 are out of our set, we're going to take the second and fourth. It's called the second and fourth minor. But you look at L22, L24, L42, L44. So we just take the second and fourth columns, second and fourth rows, we intersect, and that's called the second and fourth minor, and it's a submatrix. And that's what this Y subscript is doing. It's saying restrict your matrix L to the subset Y, to the dimensions Y. So that's what this is doing, in this case to the dimensions 2 and 4. And we'll take the determinant of that sub one there. And this is the magic formula, that the area of the volume of those vectors GI for all the points of interest is going to be given by this determinant. I'll just throw up a little bit of the math, and I'm not sure where people go with this, but this is the idea. The determinant of Ly is going to be the determinant, and this is just the definition of L. But analytical geometry gives us that this determinant is equivalent to the volume of this parallel pipe, which is just putting all the vectors together and creating sort of a generalization of a cube, but it's no longer 90 degrees, it's all angular. The volume of this object is in fact the determinant. And this is the, if we do it in one dimension, and I'll show you this for dimensions 2 because I can actually draw it. And hopefully you remember this from primary school. What's the volume of this guy? Well, it's going to be this. Let's call that U1. And we're going to multiply it by the height, right? And this has got to be a right angle. So how do we get this from this other line here? Well, there's a construction that you do. And this, let's call this one U2. U2 is this vector, and this vector is U1. What you're going to do is say U2 minus this new one is the one we want, this height. U2 prime is equal to U2 minus this part here. So if we, actually maybe we have to add it. Anyway, there's some term of it. But what's this going to be? This is going to be U1 by some factor. And that factor is given by dotting these guys and dividing by the size of U1. So that's a bit of geometry, and I hope you can see that size there by this perpendicular. And we're going to do that in, however many dimensions we have. So to get this volume, we start with the first side, any side, it doesn't matter, because this rule applies whether we go here in this perpendicular or we go here in this perpendicular. It doesn't matter. And then we look at the volume of the remaining space, and that remaining space is found by getting rid of the E1, the perpendicular in this first dimension, like we did here. So that's a rough introduction of where these volumes come from. And if you remember your analytical geometry, some of you may have done it, this is the precise formula. And this, this is like a whole lecture, 60 minutes just to do this one. So I'm not going to be going over it, and I couldn't have written it down. I had to get it in a book. But you'll find this, the details here in the big book by Taskar, Theorem 2.3 it's in. And the point is that this volume is the same as the determinant. And that's using something called the Schur complement, which, again, something I had to look up a long time since I've done it. So that's the math side of that. Back to some examples. It's amazing where determinantal point processes can appear. So in this, we're going to have a Boolean if it's true if the number drops. So here it is. The number increases, so it's off. The number decreases, so it's on. Decreases on. Decreases on. Increases, so it's off. So these Booleans here, this is actually a planar determinantal point process. And the idea is if you've just previously dropped, you expect at least an increase following. You can't have too many drops. So to prove this is a determinantal point process, don't ask me. You'll have to go look in some, 20-page mathematical text, but intuitively it seems all right. There's another one which is very computer sciencey, which I don't fully get either, but it kind of makes sense. You want a spanning tree of a graph. In this case, this edge here is similar to its neighbouring edges, incidental edges. So it turns out that the spanning trees you generate is a determinantal point process. Again, don't ask me to prove it. There's a paper, someone got a full journal article out of this. It's quite complex. But you can kind of see the idea, right? The neighbouring edges. Once this edge is there, it's going to be harder to get any of its neighbours in that tree. So there are the points. The points in this case are the edges. That's the points you're going to generate. And there it is. This is done quite late. This is only 24 years ago. So it's, it's quite recent stuff. So we've looked at the basic idea, which is that the probability of a set of points is going to be given by this this determinant of a Gram matrix. Now I'm using the term Gram matrix, which is, and it's this guy here, the Gram matrix, right? So, and it's really simple for us to kind of construct these things. All we need is a feature vector between points, and then we can get a notion of the similarity, and probably we'll have to jigger the weights, the general weights around to make it work the way we want. Yes. Yes. So yeah. Well, there's so for instance, if there's more features than there are objects, you won't have a problem. If there's less features than you have objects, that means once your points, there's more points there are than there are features, the rank will be 0. All it means is you can't have more points in your process than you have features. So, yeah. Yeah. Well, I wouldn't call it, it's a feature. So, yeah. Yeah, that's one of the, there's many. In fact, we use that property. There's a key proof that we need where that property is used. We'll see. And in fact, the way they make this work efficiently is to make sure that the feature space is smaller than the the point space, because then it does become more efficient. So.
As I understand it, you can have as many points as you have, but you cannot have positive probability mass for a collection that has more points than you have feature numbers.
Yes, that's correct. But in my case, for instance, I might have 100 documents in my object space, and the feature's a word, so I'll have 1,000 features. Won't be very efficient, but so in my case, that's not a problem. Yeah, it depends how you set it up. So good observation. That's one thing about this area. There's all of these interesting connections, and as you explore it, you kind of see them all. So it's an awful lot of fun looking at this. Right. So we're going to start with our first bit of analysis. And the first thing we have to do, all we've got so far is the probability of y is proportional to the determinant. So what's our normalization constant? Probabilities must sum to 1, so we need a normalizer. Now, this is where these guys have this amazing visualization. A lot of people have borrowed this. It's just, they've really done a wonderful job. This is one of the most interesting talks I've seen in terms of the quality of the slides. The slides are very simple. God, certainly, maybe I should learn to do this. I don't know. But so just enjoy this particular section. So we want to normalise, and that's what we've got. We know it's proportional to. So to normalise, we have to sum this over all possible sets y. And how many are there? 2 to the y, exponential. So that's a lot of sets. I hope there's a nice formula, and in fact there is. The formula is this, the determinant of L plus I, and we'll see how that comes about. So determinants, if you remember, some of you may not, are what's called multilinear. And this is the top row of a matrix. The rows are listed down here. If we multiply the top row by alpha, then our determinant is just multiplied by alpha. So it's multilinear because if we do this for every row, we'd actually get alpha to the number of rows. So it's not linear, it's multilinear. So it's basically linear in every row, or linear in every column. Remember, we have symmetric matrices. So there's the other side, it's linear in every column. So in particular, this means that you can't do this. You can't have R1 plus R1 dash, R2 plus R2 dash. Right, this is wrong. And that's what multilinearity is telling us. It's only linear for one row or column at a time. So we'll use this to figure out that formula that we just saw. This one, the normalizer. This is the secret trick. If you write it out in math, this is an example where math can be hard, but the idea is simple. So when you see these figures, you can think, oh, that isn't that difficult. But if you were to try and do the math for this and write down all the formulas, that's a lot of work. So it's a good example of making things simple in concept, but the actual. So the idea is simple, but the execution is a bit of work. So that's what we start with, L plus I. And what we're going to do is show that this ends up being the sum of all of those determinants, that 2 to the y determinants, 2 to the n determinants. We'll do it for the 2 by 2 case first, and then you can see how it works. So we're taking a determinant. So what we've got is plus 1 in the diagonal because it's plus I, right, the identity matrix. and we'll use our multilinear formula on the top row. So that's what we get. We break it up into the two. The 1, there's our +1, and there's the other bit. Now we'll do the same again for the ones below it. So we'll break up those bottom rows. So multilinearity is okay, we just have to do one at a time. But in the process, we go from 1 to 4, right? If there was n of them, we're going to go from 1 to 2 to the n. And we sort of simplify these. The determinant of this is just the determinant of this guy. Because of that big 0, there's a big 0 there. And that means that we ignore what's here for matrices. And the determinant of the identity matrix is 1. So there it is. So the determinant of L plus I is the determinant, sorry, wrong way, of all the subdimensions. 1 and 2, 1, 2, and the empty set. So it works for this case. So it's understandable. You can see it from the pretty pictures. But again, the writing out all the math is a bit of work. We'll do the 3 by 3 case. You can kind of see it's similar. And here you can see the determinant of this matrix is 1 by the determinant of the 2 by 2 here. The determinant of this matrix is 1 by the determinant of this by 1. So you can see all the parts break up. So that's our first property. We know how to normalise. So now we'll look at another property we need. It's called marginals. Just a bit of notation here. What we were just looking at, that L matrix, in the whole paper and in all the literature, when people do this, they talk about L. It's called an L ensemble. And it's a particular version of a determinantal point process. We'll look at the mappings in a bit. And this notation here, that's called a principal minor. We're taking the y dimensions of L and looking at that as a submatrix. What we're going to do instead, what we're now going to do, instead of working with L ensembles, we'll change that to what are called marginal kernels. And so instead of finding the probability of a particular set, we're going to find the probability that our set Y contains a particular set. So we're getting the marginal with respect to A. So this is a bigger probability. So if A was the set of everything, this must be pretty small. If A is the empty set, this must be 1. This is the proof for that. Now, I've got the steps here worked out. I wonder what I should be doing with that. Let me give you the sketch of this proof. This is the probability we're trying to work out. So what are we going to do? We've got our expression, there's our normalizer, and we have to sum over all y's that contain A of this determinant. Now, using the same logic as we just did before, it's equal to this expression, the determinant of L plus the identity restricted to not A, right? So let's see what, we'll use this expression a bit, so I'm going to explain to you what it is. So if A is equal to 1 and 3, and our full set is equal to 1, 2, 3, 4, I is obviously 1, 1, 1, 1, because there's 4 items, right? So I restricted to A, there's A, is B 1, 1, but we'll have zeros where it doesn't match. So this is I restricted to A, and then we're going to have I restricted to not A, which is the other part of it. And that'll be 0, 1, just swapping the signs, 0, 1. So when you're working with these guys, you've got to be dealing with these and keep them in your head. Now, if you ratio two determinants, this is actually the determinant of one matrix, right? This is we divide here, which means we're going to take the inverse inside the determinant. So that's the first step. And then what we're going to do is gradually work this down in a detail I won't go into. Remember, what we want is this formula here, the determinant of K restricted to the set A. So we want to massage our expression into a form where we've got something that is restricted to the set A. It's a bit mind-bending, but it's not too difficult. I mean, if you had to come up with the solution, it'd be hard. But you can work through these steps in maybe, 5 minutes and sort of nut them through and you figure out what you're doing. So that's restricting to the set. Which one you mean? Yeah, okay, so it's restricting the matrix here to the set A. Yeah, so it's like this one. Yeah. So what we've done is we've shown that this then, if you make that K equal to L plus I inverse, you've figured out what your so-called marginal kernel is. So this is the definition of K. And just to make that clear, there's a little section I skipped there, but this is kind of something you've got, I think it's important to figure out. Here we've got this one. But you may notice we're going to put I is equal to L plus I inverse, right? And drop that in here, simplify, so we're going to get it's equal to L plus I, let me do it the other way, inverse, no, it doesn't matter, all right. L plus I inverse, L plus I minus, I do want it the other way, sorry. Plus minus L plus I inverse. So that's going to be L plus I inverse. Taking that term, take this term, we're going to have plus I L plus I inverse minus L plus I inverse. So these guys cancel. So this expression is the same as this expression here. You've got all of these sorts of bits of matrix algebra sitting in here. Okay, now we're going to look at some of the properties of this K. And it's quite, it starts out simple, at least. So what's the probability that one item is in Y? So this is the first order marginal, right? Well, it's a determinant of KII, so it's equal to KII. So what we get is that the KII must be the probability I is in Y in our set. second order marginal, probability of I and j is being in there, determinant of this minor, KII, KJJ minus KIJ squared. Remember your second order determinant. So it's this expression. Now this is where it's interesting. This is where that... So the probability of ij being in there is always less than the probability of I by the probability of j. Well, it's never bigger than, because there's a minus something squared. So that means, in fact, that the covariance of I and j is always negative. And that's where this whole behaviour comes from, which we were talking about earlier. In the Boolean case, covariance of I and j is equal to probability I and j minus probability I, probability j. That's the definition of covariance for the Booleans. And in our case, it'll be minus Kij squared, minus. So covariance is always negative. All I've done is flip these formulas around. And that's where that behaviour comes from, right? So if 2 points have no correlation, they're a long way away. So if their feature vectors are orthogonal, when you dot them you get 0, Kij is 0, the covariance will be 0. But if two things are similar, so the two feature vectors are similar, then Kij will be quite big. And there will be a big negative covariance. So that's how things work. That's the key idea of this. But the trouble is we then, well, what about all the other marginals? 3, 4. I'm not going to get too much into the detail, but it just keeps getting uglier, right? So the 2-dimensional case is nice. The 3-dimensional case isn't too bad, but then it gets a bit nastier, so we'll just ignore that. If someone wants to look at this, there's a whole theory that some guys did, I'll point to on this, one of the papers, if someone's really into this stuff. It's quite interesting. Who knows what a determinant, or who... people don't like answering these questions. This is a determinant, right? This signature here. I'm wondering how many people know this. So this is what, if you do an engineering degree, or you do hit this in second year. It's a pretty weird looking formula. And that's how they break down all of these things, right? So, just so you know. All right, conditionals. So what have we done so far? We've figured out how to normalise our distribution. And we've got this new representation called the marginal kernel, which lets us get marginals. So now we're going to condition the next thing somebody does. What's the probability given we've given some other? We know something else. So the first one, if we're told Y contains A, what others could be in there? And this comes back to some matrix theory that, it's going to be, if you've done this, it'll be buried deep in there. You kind of remember. So I sort of recognised it after I saw it, but we'll see, some of you may or may not. But here's a matrix, K over the space of A and B. So we've put all the A guys here and the B guys in this side. You've got the restriction to A, the restriction to B, and the off diagonals. there's this thing called the Schur complement. So you type it in, look up Wikipedia, and there it is. You pop up this formula. In fact, I carry around this, it's kind of, sort of, I don't know if I should admit to this, I carry around a 60-page matrix formulas handbook, you know, and it's got all of these things in it. It's just handy. You never know when you never know when you need it. I don't know. You probably wouldn't need it, but I'm not sure. But this is something you can pick out. And in fact, this we'll see is exactly what we want to solve our marginal problem. So there's that formula. How do we use it? Well, this is what we want. So we use Bayes' theorem, right? What's that probability? Bayes' theorem. Probability A union B divided by probability A. Bayes' theorem, all right? And well, there they are, these determinants. There. We switch these to determinants. So we've got that side and this side. Well, divide them and what do we get? This other part here. So this Schur's complement gives us our answer. I'm going to give you another formula, which is kind of handy. I'll just skip this and I'll give you the two versions of it. So these are like mirroring formulas. If we take this other one and we say, well, what if A was just a single set? So, you know, we're going to start off with a big set A, a big... we're going to start out knowing nothing, Py, right? And then we're gradually going to chip away at it. Oh, hang on. You know, 2 is an element of Y. 3 is not an element of Y. We're gradually going to chip away at it like that. So we're going to, and I'll give you the formulas for that to figure out given 2 is in there. So that's the first step, and then you can go the next step. Given 2 is in there and 3 is not. So that's what these formulas here are. If we know that X is actually in there, we're just going to change K. And here's the sort of the useful part. This is X, right? So if X is in there, we know it's in there. So the probability it's in there is 1. So this is KXX is 1 here. And in fact, there's no interactions between X and the other dimensions as well. So these are 0. Very telling. If we know X is not in there, then we've got 0 here and 0s as well. But what's interesting is how similar these two formulas are. So this is our Schur complement in one dimension, which is, as we were kind of referring to earlier, what we're doing is we're normalising these vectors here so they don't contain the X dimension. That's what this is doing. It's taking out the normal, the X component in there. But strangely enough, if we include it or exclude it, it's almost the same formula. But what it means, though, is that as we include and exclude points, we just get another determinantal point process as another K. So this is a bit of magic that helps us do things. All right. Now, in this work, it's the Gram matrix that makes everything happen, right? That's our feature matrix. So we're going to look at working with that. How can we analyse it? So there it is. It's our feature vectors and then dotted, then transposed. The two sets of feature vectors. So what people propose is to break it up into a quality and a diversity section. So the quality score is a diagonal, and the diversity, these are all unit vectors. So what we're going to do is make all of these guys unit vectors and pull out their actual size onto the outside. So there it is. The phi's now are unit vectors. We've got a quality score and a diversity score. Now this is neat. What they do in learning is these things you can put a model on there, right? An exponential something or other, logistic, you know. So the machine learning guys go to town with this. This side they set up some features, whatever it is, and just hope it works. But this side they can learn because it's a nice multiplicative form. So that's how this are used. And if you go into Ben's work, you'll see some of this. In fact, they've got amazing results using these methods for summarization, and it's done by doing this kind of decomposition. So here's what you can do. You can say, well, you know, both J is a really important object, so let's increase its size. Makes the area bigger. Or these two guys, I and J, they're actually quite similar, so their diversity should be smaller, and therefore their dot product will be smaller. So you can see by breaking this down into its parts, we have an intrinsic quality and diversity part of it. But there is a problem with this. It's not all magic, because remember, it's still got to go through that rather ugly expression. K is equal to L plus I. So we've just done this to L, so it won't be wonderful, but it's better than anything else. So that's how we build these things, right? We have our quality measure, we have our diversity measure, and the diversity measure is given to us by our domain features. That's the method. And this is what we end up with. So our determinant of L is now going to be the domain feature, the quality measures, and then these here, just the determinant of the diversity part. Quality and diversity. So these guys go and there's various people with ways of dealing with this to make it work. Now, I alluded to this earlier, and this is how you scale it up. Now, what I'm not going to tell you about is how to scale this up properly. So at the end, I'll give you some examples, and it's just pulled from their slides. They're quite amazing what they've done, actually. So they get this working on hundreds of thousands, millions. You know, the dimension of Y is going to be millions. So it's a damn big matrix. But they do it by making the feature vector shorter. And then they use some other tricks, which I won't be getting into. But the purpose of this tutorial is to give you the main things, and then I'll show you some of these amazing results these guys have been getting with it. But so this is the key idea to scaling up. Well, one of them. So that's what we've got before, our quality matrix. What we're going to do is we can actually turn this around the other way. It's kind of bizarre. So that's just these two vectors flipped. And if you flip the order, right, you put these two on the other side, the Q becomes Q squared. And so this is now going to be features by features rather than items by items. So if your feature vector is really short, this matrix will be a lot shorter. And it turns out from this matrix you can get everything, right? So that's the magic. So there are our two representations, and we'll see in a bit how we do it. These are the two properties that people work with this. The eigenvectors of these are related, and that's what we'll see.
Sorry, may I ask a question?
Yes.
How you get this decomposition where the diagonal matrix multiplied by the...
How do I get
I mean,
this one?
Yeah. Is it
So,
unique or...
okay. Well, all we've done is we've just pulled out we've just normalized the original ones, right? So, so we started off with Lij is equal to Gi transpose Gj. So it's the two feature vectors dotted, all right? That's how we start. What we're going to do is we're going to pull out the size of of Gi on that side. We're going to call Ui is equal to Gi divided by the size. So this is now a unit vector, right? So you can see this?
Yeah, okay, I see. Thanks.
Yeah. So it's no big. Anyone else? But the bit to see is how you can go from here to here and how you use this, how you can use C in actually doing a computation. So we're going to do that next. So just to summarise, and this is a summary of the key math for these things. We've got several representations. We've got our marginal kernel K. Now, it's got to have all its eigenvectors less than or equal to 1, or it doesn't work. We've got our original L ensemble that we started off with. We've got our gram matrix, which we use to build our L ensemble, and then we've got this quality diversity decomposition. So these are all the parts that we put together to build these things. And there's mappings between them. We've already seen the derivation for K. And I hope you can imagine that this is when you go and invert that, it shouldn't be too difficult to imagine. And this is the matrix version of the... So forget matrices, let's just do scalars. If mu is equal to lambda on 1 plus lambda, right, L 1 plus L inverse, then we solve for lambda, mu 1 plus lambda is equal to lambda. And we're going to solve for lambda, so we're going to have mu minus, no, let me do it this way. Mu is equal to lambda minus mu lambda. So lambda is equal to mu on 1 minus mu. There we go. So that's the scalar operation, and matrices are no different. So that's the second line. And we've got this, we've constructed these, but this is the thing that makes that all work. Is K, you can put BB transpose into this formula, substitute this into this, and you can simplify and get this thing. And it's called the Woodbury Identity, you use it inside. So the Woodbury Identity is another one of those matrix things. It's the reason why I carry around this 60-page PDF that has all of this stuff, you know. Because I know this Woodbury Identity exists, I just don't remember what the actual formula is all the time. So But so what have we got here? Here we've got L, B transpose, but this is the other version, B transpose B. So the dimensions of L, we know it's going to be, L is items by items, it's an n by n. But if we go the other way, B transpose B, that's going to be features which they're calling D by D. So if the number of features is much less than the number of items, this inner matrix here is actually quite small. And to invert a small matrix is easier than inverting a bigger matrix. So if you've got less features in your feature vector, you get this construction, you get an easier matrix. You're inverting a D by D instead of an N by N, and the whole thing is simpler. So that's the basis of how they scale it up. That's one of the first versions. The next thing they do is an old favourite called random projections, which I won't go on to. There's another important concept that you really need to get this, to understand this. And the eigenvectors of L are the same as the eigenvectors of K, and that's another important property. The only thing that changes is the eigenvalues. So if L has this form here, this is a Eigen Decomposition. L inverse is equal to 1 on lambda I ui transpose, and I plus L inverse is equal to sum 1 on lambda I plus 1 mu I transpose. So that's where these things come from. And we can also do mappings, very simple mappings, between the Gram matrix form and K and L. So that's the other part that completes all of this. So what we have then is that we've got these 4 representations and we can map between them quite easily. And this dual form, which switches the order of the Gram matrix, in some cases will have a much lower dimension, and then we can compute everything a lot easier. Okay, now I'm going to give you a little bit of an intuition about an example, just an example of one of these to show you how it works. We'll do that with cycles. So let's look at this. Here's our K. We've got the U vector, the V vector, right? So, and this is what's called, this is the graph that you induce from this. So you'll see that U isn't connected to anyone else. V isn't connected to anyone else. So they're singletons, they're just by themselves. In this case, we've actually got a cycle, W, X, Y, Z. So there's W and X has a non-zero entry. X and Y has a non-zero entry. So this here represents that cycle. So that's the graph that corresponds to this. And you can see there's a simple cycle here and 2 are by themselves. So if we look at the marginal here, what's the probability of having these 4 values, this is going to cut out that cycle. So there's no cycles in there. And the determinant is just going to be composed of the diagonal parts and some off-diagonal parts, but it's only these a squared and b squared, they're the off-diagonals. So it's kind of a simpler form. If we include the cycle, then we get a term representing that cycle. So all the entries in the cycle exist. And this comes from the determinant. There's another thing we can do, which we can multiply things by -1. So we can multiply our rows and columns by -1. And it turns out that this matrix and this matrix are exactly equivalent from a determinantal point process view. And that's because if we multiply a -1 there, a -1 there, we've got 2 -1s, and multilinearity means the determinants are identical. So that's the idea of cycles, and there's a fairly complex formula that people give you for that. And I'm not going to bore you with the details of that, but it's this is, again, it's a simple idea, but it's really hard to write down, you know. But basically, you're doing this. You're saying that whenever the cycle is included in your subset, it appears in the determinant, and if it doesn't, all you've got is a bunch of terms like this.
So does it mean that we establish cycles in order to penalize the joint existence of these points? So I mean that if we do not want some subset of points to appear together, we establish cycle among them.
It's unclear the positive or negative, because the trouble with determinants is that the sign of that cycle changes if it goes cycle 4, cycle 5.
Right.
But sometimes it's positive and sometimes it's negative. That's what I'm saying. So sometimes it appears positively and negatively, but yes. So
this means that we can't directly penalize joint appearance, but we can penalize pairwise appearance.
So penalising pairwise appearance we do with
Yep.
these, but this is penalising the joint appearance, and it only comes from the cycles.
But we're not sure whether it's positive or negative, right?
Yes.
So it may appear that
Yeah, it might be positive or negative. That's the problem. Yeah, but the other thing is it's all composed of the pairwise. So the thing to notice is that I skipped over this one. Let me go back to it. The diagonals are determined by the probability of that point by the marginal. There it is, this line here. The off-diagonals, the square of the off-diagonals is determined by the covariance or the negative covariance, which is this. So you know the matrix all the way up to the sign of the off-diagonals, just from the first 2 marginals. Now, if you want to get the final, you want to get that sign, if everything's non-zero, you just need the third order marginals. But if you've got a lot of zeros in there, then you need other things. And even then, if you know these guys, you still can't determine it. Well, it's got many versions, because you can swap signs in all sorts of places. So basically, for any k, you can arbitrarily do the signs of n-1 rows. Just swap them all and arbitrarily set them. So that's what all of that's saying. Yeah. And this is the paper that goes into the ugly detail of this. It's a property of matrices I've never seen before, but if you want to really get into some detail, this is it. So these guys are, well, he at least is a mathematician at MIT, so it's quite complex stuff. But a lot of this theory was actually originally done by Chris Meek, who was a colleague of David Heckham and Eric Horvitz, who were the original Bayes net guys in the American community. So the theory of these cycles comes from Microsoft in the mid-90s. Bit of history. So we've looked at that, the cycle business, and it just gets uglier and uglier, these formulas. So now we're going to look at sampling. So what have we done? We've found the normalizing constant. We've got the different representations. We've done conditioning. So we know how to change the K matrix by saying this element's in or this element's out. So we do all of that. Now we're going to look at the important thing, sampling. So we need sampling. That's how we use these things. That's the whole point we want them. All right, I've got, here's my space of documents, return top 10 interesting documents. Summarization. Give me a good summarization of this space. This 50,000 words. Give me 1,000 words. That's a good summary. So to do those tasks, we're going to do this sampling. Or we could do a map. We could find the maximum a posterior set of points. So I won't mention the map, but I'll do the sampling roughly. So here's our Eigen Decomposition. And this is probably if you remembered one thing about matrices, this would be it, I'd say. So symmetric matrices has a nice simple decomposition, and we've got a positive indefinite matrix, so we've got positive lambdas. They might be 0. And these are an orthogonal set of vectors. So there they are. We've got some weights. We'll put the most important ones first. We'll order them like this. Now, there's something magical that happens, and this is probably the most complex proof in the entire article, is that when we take this probability of det K, we can turn the distribution into a mixture distribution over elements that look like this. So I'll talk about these magic ones here first. This is called an elementary determinantal point process. The thing to notice is that all the eigenvectors are either 0 or 1. So in this case, there's a whole bunch of them. But in this case, there's just 0 or 1. And this is an elementary determinantal point process, and it's got special properties. Now, the special property is that if my elemental point process has j non-zero, j eigenvalues that are equal to 1, its samples are exactly of size j. And this is actually how you argue that. So the expected size of these, that's a bit devious. He doesn't really describe how to do it here, but it's not too difficult. But I don't think I should be proving this. But the other one we've actually already talked about. If the rank of a matrix is size j, then, so let me do this here. If the rank of y is equal to j, then the determinant of k, the rank of k, is equal to j, which is, say, much less than our number of dimensions, then the determinant of k to the y, where y is greater than j, is always going to be 0. So if the rank of the matrix is a particular size, you can't take determinants of any bigger sets because it'll just zero out. And that's what this is saying. So the end result is that for these special elementary point processes, you're always picking j elements. And just to give you an example, here's a simple one. There it is. K is just, it's rank 1. It's just a single vector with a lambda here. So if we look at all the cases here, probability y is equal to 0, empty set, is 1 minus y. Probability of y is equal to x is going to be lambda by mu x squared. If we sum those over the x's, we get lambda, because the mu x's add to 1 because it's a unit vector. And the probability for any set of size 2, it's a rank 1 matrix, so it'll be 0. So that's all we can have in this case. For this one, as long as lambda's less than 1, we can have the empty set, and otherwise we're going to get a single point. So that's a special case. The elementary DPPs, they're sampled quite simply. And this is sort of a central point of everything. Let's go to why this is important. This is something that you have to take for granted. The proof is about a page and it's quite detailed, and it took me a while to work through it. But the idea is that the probability of, according to your K determinantal point process, is actually a mixture of these elementary DPPs. And so this is some formula that that some mathematicians at some stage worked out. And what this means is, in order to sample from an element, a DPP, we're going to sample according to these things to pick out our entries j, and then we'll sample our pj. So
yes, this is extremely elegant, but the problem is that the number of items in the summation is exponential, right? Because we sum.
Well, no, the number of these is not. So.
But we are summing over all possible subsets.
Well, hang on. Let me show you. Glad you asked. You're picking j according to this formula here. And so what you're doing is the probability that I is in j is going to be lambda j I on 1 plus lambda I.
Ah,
yeah. So this is the bit of magic, one of the bits of magic in this whole thing.
Cool.
Yeah. This is easily the most complex part of the entire paper, of the whole area. So you go and you sample which eigenvectors you're going to use using this scheme. And once you've got the set J, then you sample that elementary DPP, which is going to have this form here. Knowing J, it tells you which are in and which are out. And because it's got exactly a fixed number in, it's actually easy to sample from. And the argument is here. The probability that x is in is equal to kxx, right? But if there's exactly j in, or no, there's n. You've got n possible points. Oops, I think that is a j, yes. The probability that x is in is exactly kxx. But if you've got exactly j points in, by symmetry, the probability that x is one of the points that's in, like the first point, is going to be 1 on j by kxx. Right, so here's what it's saying. There's a nice simple figure for this. J is equal to 5. We've got j points. The probability that x is one of those points is going to be kxx. But we don't know which one. 1 of 5. So therefore, the probability x is an element of j, and x is the first point, by symmetry, is kxx on j. So that's how we pick our first point. Having picked our first point, what's happened? We know that x is in, x is an element of j for this one we've picked. And we're going, now we've got a DPP that is j minus 1, exactly j minus 1 points, because we picked one. So we go from j to j minus 1. So we've picked x, we build our k conditioned on x being true. So we go back to that conditioning formula we did a few slides earlier at the beginning, and everything, that's how we do it. So there's our conditioning formula. K, given we know x is in, is this guy. So that's the process. So that's the hardest part of this, is this particular algorithm. But the actual core of it is this step here, these two parts here. And what I found interesting is that if you actually work through these slides, it's really differently described. So I think they made up the slides after they'd written the paper, because the paper is not quite as easy. It's clearly they better understood what they were doing, because the slides have excellent material on the gram matrix. And that's the key thing, that's how you build these things. But the paper, the gram matrix is done right at the end. So, in this particular algorithm, it's beautifully designed here. We pick out j in phase 1, and then we draw a sample from j. And they actually describe the algorithm in the way I do here. Whereas in the paper, it's just a bit of magic formula, and you're not really sure what it is. So that's the end of that. We've done our conditioning. The last thing is I'm going to give you this amazing example, and it'll show you what they're using this for. So around this time, 2013, 2014, they did a bunch of document summarization, entered these competitions, and they got, second place, something like that, using these methods. So this is what started the fad, the craze, right? These amazing results these guys were getting. So here's an example, news threading. And they've really scaled this up. So they're using tricks that I still don't get yet. We've got a large news corpus. We've got lots of articles, and we'd like to do some news threads. So they're going to use a bunch of their top tricks. They're going to start with the dual DPPs, which is that dual formulation to lower the dimensions. They're going to do random projections to compute everything. There's another thing called KDPPs, which I haven't mentioned, which they do as well. But I'll give you an idea. If you want the top 10 results, how many, how big do you think your DPP, how many results should it return? If you want the top 10, 10, right? So if you've got a typical DPP, it could return 50, it could return 1,000, depending on how you set it up. But if you want the top 10 results, you know you want 10. So that's the next bit of theory that they do. They condition on knowing that they want exactly K answers, and there's some theory on how this is done that's described in the paper. So this is really pulling out all of their tricks. It's a really amazing bit of work. So this is what a dynamic topic model might give you as some of your key threads. Won't look at the details, they all kind of make sense. Here are some of the threads you're getting from their system. That's just some examples. But to show you the scale, well, actually 35,000 articles isn't that big, but it's still a damn big matrix. So they're going to use DPPs to generate stuff on here. They've actually gone and got properly evaluated content. So they're using Mechanical Turk to get people to go and say, yes, this is a good thread, this isn't. Right, so the whole thing's been humanly evaluated. And these are their responses. They're also using Rouge, which has got to be the bizarrest thing from the... have you heard of Rouge? It's in natural language translation. No. So I'll describe it briefly because it's just unbelievable what they do. So if they want to evaluate natural language translation and you want to do it automatically, you know, what's expensive? What should you do? Put some people in front of that translation and read it and see if it makes sense. Because remember, we don't have the correct answer. We don't have all possible translations. We don't have an oracle. So the best way to do it is to put a person in front of that and, you know, evaluate it. Well, they can't do that, right, yet in the natural language processing world. So what they do is they take like all 5 grams and they take the typical 5 grams in the world and then they look at the 5 grams they've got in their translation and they kind of compare them. And that's the standard for evaluating natural language. But it works. It works better than a lot of other things. So it's how they do it. So, but you can see how their state-of-the-art system with this technology they've added in there is just really doing well. And a lot of so they've entered quite a few other competitions that you'll see where they've got really good performance or someone else has got really good performance using these methods. So they've kind of become a standard. The runtime. God knows. Why is that runtime lower? Well, dynamic topic models are probably the slowest things around, right? They're really slow. But they're using random projections. They've thrown all the technology at it. K-means, of course, is brilliantly fast, but it's just such a simple method. Can't expect it to do well at this kind of thing. So that's the rather amazing sort of results that you can get with this using all of their technology, though the MATLAB code obviously doesn't do all of this stuff. It's just the basic sampling ideas. So if you want to explore that, you can look at the MATLAB. But to get these other technologies, it's God knows where it is. What I don't know is if any of the big companies are actually using this stuff. Though I do know it is state of the art for some areas. So here are the issues that people go on with this, how people turn it into something that's technology that we can use, right? So this is going from interesting theory to high quality technology. Using this dual of the Gram matrix, that's a key thing. Using random predictions. Using this KDDP with returning exactly K points. And then there's a nice map algorithm they can do. So DPPs, the search space is actually submodular. Doesn't mean too much to me, but probably might not mean anything to you. But what it means is that the search space is quite efficient. It's NP complete, but it's quite efficient. So it's not too bad. Submodularity is a property of search that became big in the machine learning community I think about 10 years ago. They discovered it. I don't know if you remember this. So that's the key things. We've looked at these different steps that make it all work. These other bits are a lot more work to get into, which is further reading for those who want to implement something. There's a rather nice way of looking at this. This makes sense to me. There's the old Chinese restaurant process, if you've seen this stuff, though all of my Chinese friends think this is a bizarre analogy. They couldn't understand it. Then there was something called the Indian buffet process, which became popular. So Chinese restaurant process was popular about 2006 in machine learning. Indian buffet process came out about 2009, 2010. People started doing these things. So Ben's introduced the determinantal point process where everyone's by themselves. So the antisocial coffee shop process.
For misanthropes.
Oh,
right?
what?
Coffee shop for misanthropes.
Yes, that's right. So I always wanted the the Mongolian barbecue process, which is where you toss everything in a pot and you mix it up, and it just. There's a famous Mongolian barbecue restaurant in Mountain View near the Google quarters that we used to go to. So there we go. That's the. But this is the key parts. It's interesting theory, and the math is lots of matrices that not everybody has, the matrix stuff, but if you're engineering, if you've done engineering, if you've done physics, if many computer science degrees have got the level of matrix stuff you need here. If you got that stuff, all of this would make sense and you'd be able to implement at least it. So we're going to start playing with this in a few areas where we're starting to think of how we can make use of these things. Because while I do topic models, what we now really understand is what we do is document summarization, like the groups here. So that's our key thing. So we need this kind of technology. So thank you for your time. I hope the bits of theory weren't too much. And there we go. So if there's any more questions, now's your time.
So any questions?
There we go.
If there are no, then let me conclude with a couple of remarks. So today we were presented some new mathematical tool, which at least for me was unknown previously, and I personally find it quite elegant from a mathematical point of view. What is good is that each time you get familiar with a new probabilistic tool, you should ask yourself several questions. How to perform sampling, how to perform marginalization, how to perform conditioning, and sometimes how to perform normalization. And here, for all these questions, there were constructive and quite elegant answers. So, which is quite good, and this means that this mathematical tool can really work in practice. So I highly recommend everybody to enrich your toolbox by including this DPP into it. And let us thank the speaker for a brilliant talk and for letting us know.
Thank you.